Hello, this study is part of our research on shell manufacturing at the Center for Natural Material Innovation, which I explore with Antiopi, Koronaki, and Michael Ramage. It examines the relationship between thin tile vaulting geometry, slicing patterns, and the produced module scale. So, current studies of shell fabrications capitalizes on high precision construction using additive or subtractive methods for manufacturing and sometimes using robotically controlled systems. However, we here wanted to actively engage with low precision manufacturing by proposing segmentation of doubly curved vaults beyond the planarization of its discrete elements. So what we're trying to do is to examine the gains from not only accepting but also accommodating high tolerance construction in the manufacturing process. Now, this study is based on a previous research that we did to explore sail and groin vaults geometry subdivision into triangular segments, where we used concrete edges for the manufacturing pieces and light tiles as the infill. The previous research focused on a small to mid-span floor system. While the same triangulation principles will be followed, this study will further investigate the triangulation computationally for a scalable pattern that will allow for a larger span. Proposing two zones for the subdivision, one central, which is A, and one at the edge, which is B. The previous research resulted in making vaults with using only two molds. Building on these findings, this study will scale the vault larger, so it's 6 by 8 meter span, and to extract the relationship between geometry, manufacturing method, and scales, as well as to observe how the scales happens linearly. In subdividing the vault surfaces, the number of non-identical elements is crucial. A minimum number of molds for off-site fabrication is preferred as it optimizes material during the production. The digital model of subdividing the shell structure is based on finding the lowest number of the molds required within a specific tolerance and accommodating it in the concrete edge. So there are two constraints that we defined for the generated vault elements to ensure constructability and efficient assembly. The first is the subsurface area. All pieces of the system should be manageable by two workers during the installations. The maximum weight of each piece should not exceed 75 kg. This makes the maximum area of each piece below 1.5 square meter. The second is the minimum edge length of the subsurface. The length of the edge of 750 millimeters should give enough span for at least 3 tiles to be placed. The typically tile length is 240 millimeters. Having smaller triangular pieces will reduce the efficiency of the manufacturing as tiles will need to be cut extensively. The variables in the studies are the span to rise ratio and the level of surface subdivisions. In the analyses, 3 ratios were studied, 1 to 10, 1 to 20, and 1 to 30. So just like inflating the vault, to evaluate their impact of the surface curvature on the level of standardization of the generated component. Once the surface was generated, different subdivisions were studied to understand how self-similar triangles can be accommodated within the surface. The area and edge lengths of the generated subdivision were then extracted, analyzed, and this is repeated of each of the generated configuration to define the number of subdivisions that meet the constraints which I introduced in the previous slides. 1.5 square meter for each triangle, and the edge length minimum is 75 centimeter. So an assessment of the variability of these geometries is carried out to provide an insight into the level of standardization. The sliced vault modules are aligned altogether, use their center point as a reference. The geometrical variability is then assessed by calculating the maximum distance of the module's vertices along the X, Y, and Z axes, and also calculating the areas. As expected, the tolerance scales linearly with the vaults ratio. The deeper the vault, the more differences the subsurfaces are. The differences are more noticeable in the sail vault than in the groin vault. Deforming along the x-axis is the largest in both vaults, as it is the direction of the main curvature section of the vault, while the deformation gets more significance in the x and z axes only in the groin vault. The sail vault shows substantial increase also in the deformation along the y-axis due to the doubly curved nature of its surface. We have identified an average subsurface against which we measured where other parts get larger or smaller. The graph here shows that in both sail vault and groin vault, the triangle gets smaller ascending to the top. While this happens smoothly in the sail vault, a more intricate pattern appears in the groin vault, especially along the groins. Now, this method is usable to understand and intuitively design in relation to fabrication tolerances. For example, say that in the studies of this scale of the vault that we are studying, if the tolerance is as high as 50 millimeter, subdividing groin vault for all three rise to span ratios can work. However, only sail vaults to a rise to span ratio up to 20 can be made. The paper shows a margin in which standardization can be craft inclusive and can mix between on-site and off-site strategies to maximize the benefit of the two. The research can develop towards enhancing this approach. For example, further studies can find irregularity range where most irregular surfaces can be defined and located. Once found, those subsurfaces can be built in-site for the sake of maximizing the standardizations of other subsurfaces. Another possibilities is for developing this research is thinking of vaults fabrication methods and finding the most suitable way for casting the concrete edge on site. Like the previous foundational research of this paper, a prototype and model can be prepared and built in the future. Thank you.